This continues the lecture on centripetal force for Conceptual Physics AB. We're going to finish this lecture with two specific application examples from engineering. The first example has to do with what is called civil engineering. One of the tasks of a civil engineer is to, for example, design, maintain, and upgrade transportation infrastructure. One of the basic aspects of our transportation system has to do with the construction of roads. For example, let's say that you incorporate a curve into a road. How do you know whether or not the posted speed limit is going to be safe to traverse that curve? This is one of the basic problems in civil engineering. Let's go ahead and take a look at the example. Copy it down into your notes. Okay, a car rounds a flat curve with a radius of curvature equal to 50 meters. The maximum force of friction that prevents the vehicle from skidding is 60% of the car's weight. What is the maximum speed allowed such that the car does not skid? Now, just to be clear, in a problem such as this, the car itself is not in uniform circular motion. It's traversing a curved path of some sort. Whenever an object moves over a curved path, however, you could always picture that path as a portion of a circle. So then therefore, there is a radius associated with that imaginary circle. This is what is called the radius of curvature. And then even though the object is not in uniform circular motion, it is still traveling over an arc length on the circle. This then means that there is a centripetal acceleration. Okay, now let's treat this problem in the following manner. Let's say that, for example, right here is the roadbed itself, and then right here is the car. And then at this particular moment, let's say that the velocity vector of the car is in this direction. So the car is then therefore kind of like coming out of the board and is traversing a curve that, for example, looks, say, something like this. There's a radius of curvature associated with that curve. So let's say that the center of the imaginary circle is over here somewhere like so, and then right here is that radius. It's given to us as 50 meters. As the car traverses the curve, it then therefore has a centripetal acceleration, A sub c, inwards towards the center of that imaginary circle. And now let's take a look at the forces that are being exerted upon the car. There may be forces exerted upon the car coming out of the board or into the board, but those forces don't matter. And the reason for this is because those forces, if they're there, are perpendicular to the centripetal acceleration, and then therefore they do not contribute to it. In this case, all that we have to look at are the forces that are being exerted upon the car in the plane of the board. In this case, then, therefore, there are three forces. Let's describe them. Okay, so first of all, of course, vertically, we have the normal force like so from the surface below and the force of gravity downwards. These two forces just cancel each other out because there's no acceleration in the vertical direction. Okay, now from the car's point of view, that would be a non-inertial reference frame. Recall that the car, or occupants inside the car, would feel a fictitious force away from the center of the circle. This then means that the car would have a tendency to skid outwards from the center. So preventing that from happening has to be a force of what is called static friction acting on the car inwards towards the center of the circle like so. So this force of static friction here, call it small f, that's what gives us the centripetal acceleration A sub c as we traverse the curve. This is what prevents the car from skidding outwards from the center of the circle. Okay, now we're given that the force of static friction is 60% of the car's weight. Here's how we write that. We're given that the force of static friction is 0.6 or 60% of the weight mg. And now let's add up the forces in the radial direction. When we do, there's only one force, and that's the force of friction. So then therefore the force of friction gives us mass times acceleration, mv squared over r. Once again, it's a centripetal acceleration because the object is moving over a circular arc of some sort, and there's a radius of curvature associated with it. Okay, now let's go ahead and do the math here. Ultimately, we need to solve for the speed v. So I'm going to substitute in for the force of static friction, what we're given here, which is 0.6 times the weight. I'll do that over here, like so. And then notice that the mass of the car, m, cancels from the expression. So whether or not the car is going to skid has nothing to do with the mass of the car. Instead, it has to do with how fast you go around the curve and the radius of curvature itself. This is assuming, by the way, that the car is, say, low to the ground. If you have a tall vehicle, such as a truck, then that truck would have a tendency to tip over, involving a rotation, which is a much more advanced problem that we're skipping over here. So we're assuming that the car is low to the ground for this reason. And now all that I have to do at this point is just solve for the speed v. So let's cross multiply the r here to the other side, like so. And then take the square root of both sides now to get the speed v by itself. That then gives us this expression here. So now plugging in my numbers then, let's go ahead and get a value here for the speed. So I now have 0.6 times 9.8 and then times the radius of curvature of 50 meters. Take the square root of all of that, and this comes out to be 17.1 meters per second. So when engineers, civil engineers, are designing road beds, they always design the road beds with a specific radius of curvature, r, such that you could safely traverse the curve at a speed that is equal to the posted speed limit. The posted speed limit is always going to be less than the maximum safe speed. Basically, the greater the speed, therefore the greater the radius of curvature. In other words, the more slight, if you will, the circle is. So if you're going down the freeway at 60 miles per hour, you're never going to encounter a tight turn on the freeway because the speed limit is large. So then therefore, in order for you to safely traverse a curve, this then means that the radius of curvature is always going to be large as well. Okay, let's go ahead and move on from there. Here's another example from engineering, specifically in mechanical engineering. Let's go ahead and take a look at an upside-down loop on a roller coaster. When you traverse an upside-down loop on a roller coaster, you are once again not in uniform circular motion, but you are still moving over a circular path. Therefore, there's a radius of curvature. Therefore, there's a centripetal acceleration. Okay, let me go ahead and do some erasing here. Let's get rid of this problem. And now let me move my file so we can read the next example. Okay, so here is that example. A roller coaster cart passes through the top of an upside-down loop with a radius of curvature of 5 meters. What minimum speed is required to ensure that the riders do not fall out of the cart? So I talked about this type of an example qualitatively in my earlier lectures on the laws of motion. Now we're quantifying it here in this example. Okay, now let's say that right here is the upside-down loop like so. And then here we are at the top like so. And then this portion of the track here has a radius of curvature associated with it. That radius of curvature is given to us as 5 meters. Okay, now let's say that the center of the circle associated with this radius of curvature is down here somewhere like so. And then here's a rider, by the way, sitting in the cart. And now we take a look at the forces that are acting on the rider here in the radial direction. Once again, we don't have to worry about any forces that may be acting in this direction, because even if those forces are there, they are then therefore perpendicular to the centripetal acceleration, which is inwards towards the center of the circle. Okay, let me draw my force diagram here off to the side. Okay, now, there are two forces acting on the rider here in the radial direction. The first, of course, is the force of gravity straight downwards, mg. Okay, but now, due to the rider's own inertia, in other words, if you were the rider, you would feel the fictitious centrifugal force away from the center of the circle. This then ultimately causes the rider to press against the seat in this direction. Therefore, the seat pushes back in that direction, and that's the normal force, like so. Once again, as we draw out the force diagram here, this is always from the inertial reference frame's point of view. It's as if we were standing outside of the ride, just watching the person rotate through the upside-down loop. These are the two forces that we would see acting on the person in the radial direction. The radial direction is like so, inwards towards the center of the circle. That's the direction of the centripetal acceleration vector, and this then is my force diagram for this situation in the radial direction. And now let's add up the forces. Both of these forces are in the same direction as the acceleration A, so I then therefore add them together. So I'm going to end up then with mg plus n is equal to mv squared over r. Okay, now mathematically, here's how this expression behaves. Imagine going through the top of the upside-down loop with a speed that is less and less. This then means that this side of the equation is decreasing. Therefore, this side of the equation has to decrease. But the person's weight, mg, is a constant. What then therefore has to happen to the normal force if this side of the equation is decreasing as the speed v is decreasing. The normal force is getting less and less. In other words, the slower you move through the top of the loop, the less tendency you have to press against the seat. Therefore, the normal force acting on you downwards decreases for this reason. If you go slowly enough, then the normal force goes to zero. So at the instant that the normal force goes to zero, this is then when you become a projectile. Here's how I can easily demonstrate this, and I'll do so once again by using my coffee can here attached to the string. Okay, in this particular demonstration, the normal force is replaced by the tension vector associated with the string. And now let me go ahead and rotate the can here in a vertical circle where the tension is a rather large value, like so. So the tension here is definitely not zero at the top of the upside down loop. However, watch what happens to the tension as I slow down the can. And then eventually, like so, the tension goes to zero, and then therefore the can becomes a projectile. Same idea here. In this case, it's a normal force that goes to zero, and at this instant, all the riders then therefore become projectiles. So now what I'll do in the equation is set the normal force equal to zero, like so. And then notice that the mass of the person cancels out. So everybody becomes a projectile at this instant. This is the minimum safe speed that we need. So let's now go ahead and cross multiply the r here to the other side and take the square root now to get the speed v by itself, like so. And then therefore the minimum safe speed is equal to the square root of g multiplied by the radius of curvature. So the square root of 9.8 and then multiplied by 5 meters. And this comes out to be a minimum safe speed of 7 meters per second. So here's how you can get a handle on what this number means. If you go through the top of the upside down loop with a speed that is greater than 7 meters per second, then the normal force is a number bigger than zero, and then therefore technically you would not need restraints in order to safely make it through the upside down loop. That's never going to happen, by the way, on a modern roller coaster. On a modern roller coaster, there's no way to remove the restraints when you move through an upside down loop. However, if you do go through the top of the upside down loop at this instant with this speed, then therefore for an instant you are in fact a projectile. If you go through the top of the upside down loop at a speed that is less than this value, then you definitely need restraints to keep you safely inside the ride. Okay, I'm going to go ahead and conclude this video here. This also concludes the problems that we'll have associated with centripetal force.